7, where we're going to talk about greedy algorithms for the only time in the entire course. But I'm sure you'll all enjoy it because greedy algorithms are way easier than the other algorithms. For some administrative stuff, which I'm sure you've all seen, is I'm releasing the midterm exams after lecture. You can pick those up for me at office hours. I'll say more about the midterm exam once we get there. That's pretty much it in terms of admin. Also, you probably noticed there's no homework this week. I really wanted to, but I decided not to just to give Rahul more time to finish the other grading, which homework 2 is also finished grading. So yeah, there's no homework, unfortunately. I'm also going to have an extra lecture, like over Zoom or something, to make up for the very first Wednesday of class / also last class we missed. So there will be one more lecture. I haven't decided yet if it's going to be like material you need to know, if it'll just be fun material, or if it'll be a review. But there'll be something like that, probably over Zoom. Okay, so that's pretty much it. Any questions about the course in general, other than the exam, which I'll talk about in detail later? Yes?
I know we got a slight rough outline at the beginning of class, but now that we're about halfway through, do you have any more structure to how that class might end? I guess with the final and the end date or whatever.
Yeah, so for getting on the calendar. So I think the last day of class is a Wednesday, and it's August 4th or something. So the Monday before that, we'll still have lecture. In terms of the topics, those are going to be the same as Canvas lists. No change has happened to the topics other than we swapped greedy with graphs. But yeah, so the final exam will be held probably on Wednesday if it's in person, or it'll be online. I'm still thinking about it because it'll depend on how well you guys do on homework 4 and the midterm. Because if I make it online, it's going to be harder than if it was in person. Because the in-person exam, I just basically copied textbook questions you could have Googled online. So obviously I can't do that again if it's online. So I'll have a more concrete answer after homework 4 has been submitted. But yeah. I mean, obviously, if you have an actual conflict with taking it in person, we can work something out. I've done that with a couple students who missed the midterm Monday. So if you're asking because you might have a conflict coming, then no worries, just email me. If you're asking because you have fear of exam, fair enough, I don't have an answer. Any other questions? Yes? No idea. So it depends on how far we get. So my intention is it'll probably be the actual last lecture. It'll be more of, you don't need to know it, but these are cool future things you could study in algorithms if you care, online algorithms, game theory, stuff like that. That's my intention, but obviously if we're going slower through max flows, I'll use that to cover more max flow stuff because that stuff's important. Any other questions? Okay. So today we're covering greedy algorithms. I've made a much smaller list of problems this time, and I'm hoping we can actually cover them all. And these are all very practical problems, so I'm sure they'll make sense. But first, I wanted to talk about this idea, which is adversarial reasoning. So we've talked about worst case analysis before, and that's just, when you're looking at your running time of an algorithm, assume you're given the worst case input, and you need to do well against that. But there's a more general idea, which is just thinking adversarially. So pretty much anytime you're given a problem, you want to think of there's some adversary, or you have some arch enemy who's trying to make you lose. So you have an enemy who wants you to lose. Now, what does lose mean? Depends on the context. So a couple examples, there's the obvious one, which are like games. So you could be literally thinking of a game, like chess or something, and you have an optimal, you always assume the player you're playing against is perfect. Because if you can beat a perfect player, you can beat any player. So that's why we assume that. So for an example for games, we assume perfect opponents. But there's other examples like in machine learning. So for machine learning, you need to collect data. And the idea here is the way you think about it adversarially is the adversary has the data, and he's going to charge you a ton of money for that data. So because the adversary owns the data, and so it's expensive, you need to use as little data as possible. And for general algorithms, you could think of like running times. So here you imagine you're playing a game where you create an algorithm, you give it to your opponent, and then they're going to figure out an input that breaks your algorithm. Either makes it slow or makes it inaccurate. So as we'll see later in the course, sometimes we consider algorithms that have errors. They don't always have to give you an optimal solution. So for cases like that, your opponent's trying to find the solution that, or the input that breaks your algorithm and makes it incorrect or makes it slow. So in that case, you're thinking about how can I make a robust algorithm, an algorithm that no matter what my opponent gives me as input, it'll still work correctly. So those are just a couple ways adversarial reasoning comes into computer science. It's pretty much the dominant trend. You see this kind of everywhere, especially in ML. Like ML is just dominated by adversarial reasoning. So that's just a kind of general tool, just a way to think about these problems. And it's the same for when you're doing proofs. So when you're doing proofs, I've been kind of mentioning this idea of think about what could go wrong. So maybe you're not confident your algorithm's correct. You can just think about, well, what could go wrong? If I get this special edge case, what will happen? And if you think in that way, well, you'll see, oh, wait, that's OK because my algorithm does X, Y, Z. And then that gives you your proof of correctness. So in all these cases, using this kind of thinking mechanism can simplify your life. So just wanted to mention that again, so we keep remembering. Anyway, tape sorting. So this is the first problem we're going to talk about today. It's a very natural problem. So I want you to think of this thing here as a bookshelf at a library. And each of these numbered things here are books. And you can see book number 2 is a thick boy. This is like a dictionary or something. It's just a massive, massive book. And so in this scenario, you've gone to the library. You're trying to find some book. And how do you find a book? Well, you have to physically scan from left to right, assuming they're alphabetically sorted, to find whatever book you're looking for. So the total time it takes you to find the book you're looking for is proportional to how wide these books that come before you are. So if there's just a massive book that takes up a whole shelf, you have to walk through that whole aisle to finally get to the book you're looking for. Another way to think of this is, and the way we will talk about it, it's called tape sorting. So back in the day, hard drives used to be physical magnetic tapes that basically looked like this. And instead of random access, to access a file, you physically had to move the head of your reading machine from left to right until you eventually hit the file you're looking for. So that's kind of the setting we're thinking of here. Is there something you want to find, some book or some file in a system, and the way you find them is by physically moving something from the left end to the right end until you hit it. And in particular, in this problem, you're given a length array, L, where L of I is the length of the file stored at location I. So you could think of this as the length being in time. This is the time it would take you to read through it. You could think of it as a physical size, like in terms of meters or something. Doesn't matter. That's some length that we're going to be using. So any questions about the setup of this problem? Okay. So when in doubt, just think of the bookshelf example. Very physical and intuitive. So we can talk about, and we can give a formula for the total or the average access time. So on average, how long would it take us to access all the files? Well, let's just assume a uniform distribution, so each file is equally likely to be requested. All you really need to know is that means 1 over n is there. It's the only thing that matters in terms of distribution and probability. So the average access time is for each file, k. We're going to sum over every possible file k and sum over the cost it takes to read k. So the cost it takes to read k is the sum of all the things up to and including k of their lengths. So for example, here, if we're looking at cell 3, the cost to read 3 is the cost to move past 1, the cost to move past 2, and then the cost to move through 3. So in total, it would be L1 plus L2 plus L3. Okay? And then we're just summing that over every access for every file. So in particular, the first file is easy. You only have to read it. You don't have to read anything before getting to it. So any questions on what average access time means? Yes. So for the average access time?
Yes, for n.
Oh, and yeah, n's the number of files. So it would be 5 in that case, because there's 5 files. So I'll just say that, n is the number of files. The idea behind average access time is you could think of this over the lifetime of a system. It's every access that's going to happen. So you're considering every possible file. Some files could be accessed more than others, but here we're assuming they're all accessed equally frequently. Any other questions? Is the problem statement, well, I guess I haven't told you the problem statement. So here's the problem statement. So we can improve the average access time. We can make it smaller by reordering the files. So why is that? Well, intuitively, having 2 here, file 2 here, is greatly increasing our access times because all of these files have to wait through this monstrous one to get read. So every time we read any of these files, we first have to wait through reading file 2, which takes forever. So if we moved file 2 to the back of the list, that's going to improve the access times of 3 and 4 and 5. So we could move to the end to improve access times. Okay? So we can do that. So of course, as optimizers, we're going to try to find the best one. So formally, we're going to pick a permutation of the n files. So this notation here means the set 1 through n. And we're picking this permutation. Now, all you really need to know about permutations here is it's a function, and pi of I gives you the name of the file stored at position I of the tape. So in the original, we have file 2 is stored at location 2, but if we swapped it with file 3, so if we did like a swap here, then we would have pi of 2 equals 3, and pi of 3 equals 2. So the thing stored physically at the second position is now file name 3. And similarly, the thing stored at the third position is the file named 2. Okay? So these locations and the files stored at them do not have to be the same if we use a permutation. So the permutation is just modeling the reordering, basically. And then, of course, our goal is to pick the permutation pi. We want to pick this pi to minimize the access cost, the average access time for that specific pi. Okay, so any questions about the problem setup now? We're basically sorting the tape. We're moving the files around so that the average access time is minimized. Yes?
So the permutation just like a reference book to show all the links, like which file in which position?
Yeah, you could think of it that way. So pi is essentially an address book that tells you at this home who's living there, which file is living there. Yes. That's kind of what we're going to do. Kind of. So, okay, it sounds like we want to think about how to do this. So let's think of some ideas. What's just your natural first gut instinct? Just from looking at the picture. How would you sort the files? Okay, cool. So everyone's first instinct was a greedy algorithm, which I knew was going to happen. So, I mean, everyone suggested the right answer, so it's just sort in increasing order of file size. So which means shorter or smaller lengths first. Okay. So this kind of makes sense, right? So if we have a bunch of short files at the beginning, so let's say we redrew this, and we had, 1, 3, well, actually, let me just do it exactly. So the small ones are 1, 3, and 4. So this is going to be 4, 3, 1, 2, 5. So this makes sense because every time we're going to access a file, we have to go through all the first ones first. And now the first ones are all really small. So in particular, every time we access any of 4, 3, and 1, they'll be super fast now. If we need to access 1, we're doing less work than accessing all of 2, just through those 3 files. Now, if eventually we need to access 5, we're still going to have to run through everything. But that's okay because on average, we've reduced the time it takes to access a couple of them. And so the overall time is also reduced. So I'm just kind of articulating why you might have thought to do this strategy. Oftentimes we think of greedy algorithms and we don't even know or think about why they work. We're just kind of like, it just pops into our head. So you kind of want to think about, at the very base level, why we chose that, why we made that decision. Okay, so another way to describe this algorithm, and we don't have to, this is good. We're going to store increasing order file size. Okay. So who thinks this algorithm actually works? There's no issues. Okay, one person who read the textbook. So think about what could go wrong. Yes?
Our largest is the most frequently accessed.
That's a great point, except they're all equally accessed. But save that consideration for the next problem. Any other concerns? You might not have concerns, but I just want you to think about it. Okay. So it does work, so we need to prove it works. Because like usual, if you give a greedy algorithm, you need a formal proof of correctness. So let's prove it. So here's an easy way to prove this. If we want to prove the sorted order is optimal, another way to say that is any adjacent pair is in order. Because if each adjacent pair is in order, by induction, the whole thing's in order. So we can just focus on a specific index I and its neighbor to the right. So let's, for simplicity, we'll let A be pi of I. So that's the file stored at location I. B equals pi of I plus 1. So if we draw our picture, we're somewhere over here, index I and index I plus 1, and the files stored are A and B. And we're going to do this by contradiction. So suppose that the length of A is actually greater than the length of B. So in the picture, let me adjust it. So now A is bigger. So we want to somehow show that if we didn't do this, we'd get a better solution. So in particular, let's consider an alternative solution that has B go first and then A. So what we've done here is a swap. So this original solution I'll call O because it's some optimal solution. We're going to assume it's optimal. And then this is some O prime. In fact, we can just call it G for making a greedy choice. Okay. So notice if we make this swap, the average access time does not change for anything over here. Why? Yeah. So this is just because in order to get to these files, you have to go through both A and B. And it doesn't matter if you go through A first, then B, or B first, then A, because either way, you're doing L of A plus L of B. And addition is associative and commutative. Similarly, everything over here also won't change. These will also be the same. So the only way the costs can change are for the access times for A and B. So only access times for A and B can change. So we can focus on just the access times of A and B. We don't have to worry about everything else. So let's do that. You can even imagine those were the only two files if you want to. So when we do this swap, what changes? Well, we've made the axis time of B smaller. So we've decreased the time for B by L of A, but we've increased the time for A by L of B. So in total, the solution has the same cost. So the new cost is the old cost plus L of B minus L of A, and we're going to divide it by n just because we're looking at averages. Does that make sense to everyone? Does it not make sense to anyone? So this is the key step. Yes.
You labeled the top one optimal. Is that like we assume that's what we're going to contradict it?
Yeah. Yeah. At least for this one, we're going to contradict it. In general, we'll do something slightly different. But this is actually true for any solution. I just want you to think about it for an optimal to get the idea. Okay, so the new cost is the old cost plus this quantity. But what do we know about this quantity? Remember, we're assuming that L of A is greater than L of B. So if we rearrange that, that means L of B minus L of A is less than 0. So in particular, L of B minus L of A divided by something is also less than 0. So this is strictly less than old cost. But the old cost was optimal. Contradiction. Or another way to say it, if you don't want to use contradiction, you could just directly say the new cost is better. And so that's true. So you could do it directly or you could do it by contradiction. I just personally think contradiction is more satisfying. So that's pretty much the whole proof. We can kind of squeeze it on one page. Any questions? Yes?
Why did it need to be divided by n?
That's because we're looking at average axis costs.
But n is the total.
It's the total number of files. So this is just an artifact of that n right there. So when we're looking at the average change, we have to divide it by n. But that part's not super important. The important part is that you have L of B minus L of A. Yes? Yeah, if you want to generalize this to saying the entire sorted order, then yeah. So this tells you for a specific pair, they have to be in order. And so by induction, all pairs have to be in order. Which implies the whole thing is sorted. But that induction's like really easy, so we usually skip it. The hard part is this part, where you do the exchange. Once you have the exchange part, you can, mechanically throw it into induction. Any other questions? So we're going to basically do the same thing 1,000 times. So if there are any questions, please ask now. Okay. We're going to slightly generalize it. So, as was hinted before, we now consider what if there are frequencies. So instead of looking at the average now, we're going to define the total axis time. So we're assuming here that f of I, this thing tells you the total number of times I will ever be accessed. So over the entire lifetime of the system, that's how many times we'll try to find file I. Or you could think of this as the total number of times you're going to try to check out a specific book from the library. Maybe there's a couple times in your life you'll have to research the same idea, and then after that, it's done forever, and you'll never have to check out that book again. So given the frequency array, our total axis time, the only difference is instead of 1 over n, we're going to multiply each file by its frequency. So if we are going to access the storage location, the file at storage location pi of k, then we first need to run through all of the files that are at the storage locations from 1 up to k. So this is the same. This is exactly the same as before. This is the same cost. But now the frequency is different. So instead of 1 over n, we have this function, or this array f, that tells us the number of accesses. And then you can rewrite it like this for convenience. Okay. So any questions on this version of the problem? So for example, you could have some files, some books that are really niche and no one reads them, and so their frequency might be 0. No one ever reads it. But maybe you have a really popular book, like the Lord of the Rings series, and then the frequencies are super high. So the first thing to think about is, will the same greedy strategy from before work, which is sort by length? Will this still work? And if it doesn't, try to think of an example. A simple example with 2 files where it wouldn't work. Yes.
Well, if the shortest files are never accessed, then it wouldn't work.
So let's think of an example where you have A, B, and A has frequency 0, B has frequency whatever that is. So now what's the optimal way to sort it? Well, if we sort it by length, it would look like this. But if we swap them, now the access time for B is going to go down. The access time for A goes up, but we never access it, so it doesn't matter. So this is a better solution. So that's our first example of a greedy counterexample. You'll have to make these a lot. Pretty much every time you make a greedy algorithm, you need to do this thought process. You always want to think of a counterexample. So why would you do this? Well, obviously, if you find a counterexample, your algorithm doesn't work, you can't use it. If you can't find a counterexample, you'll probably think about it and figure out what the proof of correctness is. So that's why you want to do this. And you'll be asked to do this countlessly, many times. Okay, so we know sorting by length doesn't work. What about sorting by frequency? What about this one? Does that one work? Seeing people just saying no, but why? What's the counterexample? There could be something similar to that. Yes.
I think if you have b that is 100 to the 100 to the 100y,
Mm-hmm.
and then a really skinny a, and both are used about the same, but b is used just slightly more, and you could put more books after that if you wanted to make the penalty greater.
So basically, that one that's a counterexample for the other strategy is a counterexample for this one, just in reverse. So here, the smaller one, it's way smaller, and it's accessed only slightly more times than B. So if we did swap them, you're going to increase your costs by a lot. So for this one, you don't want to swap. So sorting by frequency doesn't work either. Any other suggestions?
So by frequency times,
Times length? Okay, so let's think about this. So intuitively, we have two competing I guess, parameters. So we want the lengths to be small first, but we want the frequencies to be high first. So we want high frequency and low length first. So how can we combine these two things? One way would be to multiply them. Well, so let's say we did that. So we had frequency of I times the length of I. We're going to sort by that. Does this ensure that things that are small length go first? And does it ensure things with high frequency go first? So if this has very low length, this will be small. So if this was like 2, it'd be small. But if this is high, which is what we want, it'll be large. So high frequency will actually hurt us with this quantity. So just based on what we want low length, so let's put L of I. We want high frequency, so let's divide by f of I. So this ensures things that are small, length, will have a small numerator, so the whole thing's small. If it has high frequency, then it has a large denominator, which makes the whole thing small. So now both of our parameters are moving our solution the way we want it to. Okay, any questions on that? So the new algorithm is going to be sort by length over frequency. So this rewards high frequency, low length. Yes?
So would it be possible to use the approach like the length of
Some function of it or exactly that? I could argue this is a function of that, so yes. So this is just L times F divided by F squared. So in general, there's no exact recipe, but if you just look at most of the correct greedy algorithms, typically they're ratios. So another thing we could have done is do L of I minus F of I. That does the same thing. It rewards small length and penalizes small, or helps, high frequency helps for this. But kind of the issue with this is they're unbalanced. So for the ratio, you're kind of taking them equally. For this, you could have like 1,000,000 frequency and a length that's like 2. And these two numbers are kind of clashing. They're in different scales. And so frequency will just dominate, and you're basically ignoring the length. So that's why ratios are usually better, because it has this nice scaling. You're treating both quantities equally in a sense. But there's no catch-all. Sometimes you'll want to use the second one. It just really depends on the problem. But a good rule of thumb is to use ratios. So ratio or multiplication is a good rule of thumb. Because preserves scale. Okay. So that's the algorithm. So we're going to do the same thing again. It's just going to be harder this time. Because this thing is a monster. So again, we're going to let A and B be the first and the second file respectively. And we're going to suppose, for the sake of contradiction, that they are out of order. Okay? So we want to have the same picture in our heads again. So we have A, we have B. A is not necessarily the larger one, it just has the larger ratio. So that's important here. This is I plus 1. And then again, we're going to consider a swapped version, which has B first and then A. Okay, so if we do this, what's going to happen? So how does the cost of A change? Well, just as before, it's going to get bigger by L of B because we move B in front. And similarly, the reverse for the other case. Now there's a slight difference. Yeah, the time. So how frequently do we access file A? Well, that's just going to be the frequency of A. And how frequently do we access B? Frequency of B. So this time, the new cost is equal to the old cost plus a difference of L of B, F of A, minus L of A, F of B. So now what can we say about that? So remember, we supposed for contradiction that formula up there. So maybe we can rearrange that formula. So if we, so let's look at this formula. So let me rewrite it as L of A divided by F of A is greater than L of B over F of B. So let's try cross multiplying. That's going to give us L of A times F of B is greater than L of B, F of A. And now if we subtract, we'll get L of B, F of A, minus L of A, F of B is less than 0. Everyone agree with that algebra? I hope so, because almost every time I teach this, I mess it up. But I think it worked this time. It's a miracle. Okay, so it's less than 0, right? So we're in the same situation from before. So this will be less than the old cost, because this thing is less than 0. That's a contradiction. So any questions on this proof? So it's the same idea from last time. We're doing a swap and then seeing how the cost changes. It's just now we have this frequency parameter that we have to take into account as well. And so the algebra gets a little messier. I'll also point out there's it's a cool fun fact about this. Because we showed this lemma is true, the cost is minimized when that happens. And in particular, if you didn't use this order, it's strictly worse. So not only is the greedy algorithm optimal, it's the only optimal solution. And this sometimes happens. When it does happen, the proofs are easier, always, because you can use contradiction. So any other questions about tape sorting? Yes?
You wrote increased cost of B by L of A with B decreasing.
Yes. Yep. That is why there's a minus. Other questions? So you'll notice the main thing here is the algorithm itself is one line. It's basically 4 words. That is the easiest algorithm we've seen in the entire class. The downside is the algorithm took some work to prove. And technically there's an induction here that I didn't even show, but it's kind of mechanical. So greedy algorithms, the benefit here is it's very easy to describe. The idea is very intuitive. The downside is usually there's a trade-off between the proof complexity and the algorithm complexity. So there's a trade-off between alg complexity and proof complexity. So usually, so for example, in general recursion, like divide and conquer, the algorithm itself is basically the proof because you design the algorithm with the proof in mind. The recursion is the induction hypothesis. Whereas here, there's not really a tie between the algorithm and the proof. And so coming up with the proof is usually harder. And some of these greedy algorithms have very hard proofs. So this is the main downside to greedy algorithms. And then the other downside is obviously they're not even always correct. So even when it is correct, you still have this change in difficulty. So greedy algorithms aren't necessarily easier because you're just pushing the work onto the proof instead. Okay, so the last thing is yes.
How would you characterize the running times of these algorithms?
I was about to say that. These are usually faster. So what's the running time of this algorithm? Or just give me one running time, because we didn't really specify how we're sorting it. O of n log n. So the best sorting algorithm in general is O of n log n, so that's the running time of our algorithm. All we really have to do is sort that quantity, computing ratios, whatever, that's constant time. So it's pretty fast. N log n is almost the best you can do. Because we have to do a sort. Sorting takes O of n log n. Never use radix sort. It's cool. The running time was easy. Yes.
So like, on like a homework or exam or something, where you said there's an induction that's like mechanical that you're not doing, would this be fine, or do we have to do that induction?
No, you don't need the induction. So this is called an exchange argument, which I'll talk about more thoroughly after the next example. But you just need the exchange argument part, and then the rest kind of mechanically follows. But it depends on the problem. So it depends on the problem. But most of the time, just this part's fine. Yes.
So I can imagine a greedy algorithm where every step we think, what if we took all of the next books there and then choose the best one from the end?
Mm-hmm.
And that feels massively slow.
So
Do you know if that would be anywhere comparable in speed?
yeah, so I thought about it last night. Could you do this with dynamic programming? And the algorithm you described is the same one. That's like the standard one. That one's exponential time, and I can't think of how to improve it. Because basically for any choice of the last book, you have to remember the other books. They're not like in order. So if you picked the last book and you moved it at the end, well, now you're remembering like a subsequence of books at each step, and so it'd be exponential time. I'm pretty sure there's a way to like improve it, but there's not like an obvious way. There wasn't like an instant, oh yeah, this is how you do it. But great question. You can almost always solve greedy algorithm problems with DP. They're just usually slightly slower. So my guess for this problem is that the optimal one would be n squared. I just don't know what it is. My intuition says you can do it with n squared. But we'll see more examples of that. Okay, so let's look at the next problem. This one's course scheduling, which is something you've all have done before. So in this problem, you're given two arrays, S and F. S here represents the start time of course I. F represents the finish time of course I. And your goal is to pick a schedule of non-conflicting courses. And you're very ambitious, so you want to pick as many courses as possible in one semester. You're trying to maximize those credit hours. So formally, what does it mean for something to not be conflicting? Well, either course I starts after course I finishes, or course J starts after course I finishes. So if we know either of those two conditions, we know their times cannot overlap. And one way to see this is visually. We can represent the courses as intervals, where this is SI, this is FI, and then visually they overlap if they overlap physically. And you can see in this example, if this is course J, then the start time of course J is between the start of course I and the end of course I, and so they're overlapping. So in this example, the blue blocks, this is one particular schedule you could choose, and it has 5 courses in it that do not overlap. But they are back-to-back, which kind of sucks. But you don't care about that, because you're addicted to caffeine. Okay. So is the problem clear? I hope it's clear, because I'm sure you've all faced it. And today we will solve it once and for all. So how do we pick the maximal set of courses that don't overlap. So I guess first let me give you the DP solution. Try them all how? What's the, try what? I heard something that sounded right. Not quite. So we need to have some kind of decision. What's our decision? Yep, so that's one. So let me rephrase it slightly. Do we take the first course? And then, of course, the sub-problem in general would be, do we take the ith course? That's the general sub-problem. So either we take the first course or we don't. We recursively figure out how big the schedule would be in both options. And then pick the best one. And another way you could do it is what's the next course? So just like longest increasing subsequence, you could instead say, okay, we've already committed to taking course I. Now what's the next course we should take? And then you could scan over all possible next courses if you want. Okay, so that's the basic idea for a DP solution. The final answer will be O of n cubed. I urge you to think about how to get that, but we will not focus on it. So is there another way we could do it? What's your natural instinct for how to do it? That's one option. That's a great option. So we could choose the course with smallest total time, or I'll just say time interval. I hope everyone gets what that means. Remove all conflicting courses. And then recurse. So this is a general schematic to describe any greedy algorithm. Do something greedy, remove conflicts, recurse. You can also implement this with a for loop, because for loops are recursion, but this is probably the easiest way to think about it. Okay, so let's think about this algorithm. I'll even do it on this picture. So what's the smallest one? I'm going to say it's that one. Let me use orange. Okay, so we picked that one. We have to kill everything that intersects it. Okay, so those are all gone. The next smallest is going to be something like that one. Kill everything it touches. So what do we have left? Well, out of the small ones, we have this one's left. Kill all those. So right now we have 3 things in our solution. We include that one. And then this one. Well, that's interesting. So actually that's the same solution as this one. Cool. So that's what that algorithm would look like. Yes?
Do we need to add priority to ones that conflict with less classes?
That's a different algorithm, but you could do that for sure.
But the shortest first is definitely the best because it does minimize conflicts.
Are we sure?
If you have one that intersects everything, what is the shortest?
So here's an example. So what would we do in this case? We would take this one, right? It's the smallest, and that's it. But instead, we could have taken the two long ones, right? So that doesn't work. Other ideas. There's a lot of greedy algorithms for this problem. You'll probably see 5 of them in the homework. Actually, in discussion. Yeah, in discussion, you actually go through, I think, 7 of them. And 2 of them work. And this is one of them that we proved doesn't work. Other suggestions?
The one that finishes the soonest.
Finishes the soonest. So shortest F time. So we can also sort by F of I. Pick earliest left. Remove conflicts. Recurse. How do we feel about this one? So first, I urge you to think about why it might work. Like, what's the rationale that could generate this? So if you do this, you're giving yourself the most future options. Why is that? The thing that finishes first is going to conflict with very few of these blocks. So in the future, you're left with a larger time span of courses to pick more things. So it's the risk-averse strategy of giving yourself the most future options. So that's intuitively why this could work. Does anyone think it doesn't work? So it does work. So here it is. There's 2 versions, one's pseudocode, one's a picture. I prefer the picture. So the way this works, let me actually make this bigger. So the first thing is you take the blue one that ends first. Here's the line of conflicts. So all those things are gone now. The thing that ends first after that isn't in conflict, is the next blue one. And we continue taking things and recursing. So ultimately, we're just literally sorting all of the intervals by F and just going in order of the sorted order. We pick the first one, remove the conflicts, do it again. So it's recursion, but you can also implement it with a for loop, just doing the same thing. So just saying at any moment in time, I, if the current start time is later than the previous finish time, that means that's not conflicting, then we consider it to be added to our set, and we do add it. So this is the first non-conflicting interval. That's all that's saying. And then once we find the first non-conflicting interval, we add it. Because since we sorted in advance, we know that's going to be the smallest finish time left. Okay? So you could do it with a loop, or you could just say what I said up here. Recursively, they're the same thing. One's one line, one is more. So, it's preference, I guess. But if you're getting comfy with recursion, I recommend the first way. Okay, so any questions about what the algorithm's doing? Yes.
What if we choose the class that starts as late as possible? Is that the same thing?
It might be. I urge you to think about it. I won't answer it just because that's on the discussion problems. But you should definitely think about it. You're in the right ballpark. Okay. So we need to prove this thing's correct. We're going to use a similar strategy. It's almost like the DP strategy. So remember, the DP strategy said, what's the first class? Here, we're answering the question. What is the first class? Well, it's the one that finishes first. So this answers the DP question. So whereas DP tries them all, we try one. We're not going to try them all. We just say, this is the answer. This is what we're going to do. So instead of the complexity being in the algorithm, the complexity is in our thought process and in the proof. So how do we prove this? Well, let's just pick a schedule. So let X be an optimal schedule. Okay. So X is some set of intervals. Not necessarily in any order, but because it's an optimal schedule, we know there's no conflicts. Right? So now let's just say that C in X is the course that finishes first amongst those in X. So if we just compared all the finish times of these, so if these are the finishing times, then we would be looking at this one. But it does not have to be the smallest finish time in the entire list of intervals. It's just with inside X. Okay, so how can we use this course C? Do we know anything about C versus the greedy option? So let's call G be the course that finishes first overall. Can we do anything with G and C? Did someone say they're equal? So they don't have to be equal. But if they were, how would you prove they were equal? Think about that. So we're going to do something similar like we did in tape sorting. We're going to consider a new solution. So before we swapped A and B to make a new solution, now we're going to modify X. So let X prime be X, where we remove C, but we add G. So first of all, X prime has the same size as X. We remove one thing, but we added one thing. So we know the size of X prime is the same size of X. So if it is non-conflicting, it's optimal. So the question is, are there conflicts? Could there be any conflicts? No? Why? Okay, so let's say for contradiction, suppose, let's draw G So this one's G, it finishes first. Then you have C, maybe C's like this. So let's say G conflicted with something in X. So let's say we have something that G conflicts with, but does not conflict with C. So it has to look like this for it to not conflict with C. So if it's in X, we know it doesn't conflict with C because X is non-conflicting. So this is in X, so can't conflict with C. So what's the issue? Where's the contradiction? So C is not the one that finishes first, that's true. But what else is true? In X, but what else is true? Overall, right? The main issue is E finishes before G. But our greedy algorithm says G is always the thing that finishes first. So this contradicts the greedy algorithm. So I'm emphasizing it's G and not C because the fact that C is the first, that's just an artifact of this specific proof. But in general, for problems, this won't be the case. In general, you're trying to show it contradicts what the greedy choice is doing. So here, if this E existed that conflicted with G but not C, well, it would have been the thing that finished first, and so G would have actually been equal to E. Or you have a contradiction. So because of that, we know nothing conflicts with G. So this implies nothing conflicts with G. And so we know the rest of X has no conflicts with itself. So this implies X prime has no conflicts. Okay? So overall, that proves that the first greedy optimal choice is in some optimal schedule, specifically X prime. X prime is an optimal schedule that contains G. So any questions about that? Yes.
What if G conflicts with C? How are we showing that they're the same?
That's okay if G conflicts with C. We're removing C from the set and adding G instead. So the reason I drew it like this was to emphasize the fact that if E does not conflict with C, but does conflict with G, then we have this particular kind of contradiction. Yeah, C doesn't have to conflict with G, and if it does, it doesn't matter because we're removing it from X to construct X prime. Yes? No, we don't even need that. So I just did that because just mathematical intuition told me to do that, but C could have been any course in X, and this still was true. Yes? They were both. So X and X prime are both the same size, so they're both optimal, but X prime contains G. And what we're trying to prove with the lemma is that some optimal solution contains the first greedy choice. And now that we know some optimal contains the first greedy choice, by induction, there's an optimal that contains every greedy choice. So by induction and the lemma, there exists an optimal solution that contains every greedy choice. Now that doesn't mean it's optimal just yet. So what we showed is there's some x for which the greedy solution is contained in x, but that doesn't mean they're equal. There could be something in x that's not in g. So how could that happen? If there exists something in x, but not g, in particular, that's true. So there exists in c and x, but not g. What do we know about this c? So could we add c to g? So if can't add c to g, there must be a conflict. But c is added to x, which contains all of g. So if it conflicted with g, it would conflict with x, because x contains g. So if this happened, that's impossible, and you could add c to g. But naturally, the greedy algorithm is going to keep adding things as long as they don't conflict, and so it would have added c. So that's the idea. We're going to make it formal in a second. But ultimately, this proof is really highlighting the optimal substructure of the problem. So it's saying if we make the optimal first choice, we pick the best first course, and then we let the recursion fairy find the optimal rest of the schedule, then if you just tag those two together, you get an optimal for the entire problem. So this proof here by induction is really using optimal substructure. So the best first course that's the wrong course, plus optimal schedule over the rest gives you an optimal schedule overall. So that's the optimal substructure. And we're exploiting that in the proof here. To do the induction. Okay, so that's the idea. Here's the rigorous version. Usually this is sufficient. So if you have optimal substructure that's clear in your problem, then you can do something like this. Just, obviously you've got to spell out the induction, but other than that, it's almost this easy. But here's the unrolled version, and this is why you shouldn't unroll induction, because it gets terrifying. So this is going to have an induction inside the induction. So we're going to start by assuming this is the greedy solution. And we're going to consider some optimal solution. And in particular, we're going to consider the first time the optimal solution and the greedy solution diverge. So this one's optimal up to this point. The greedy and optimal are the same. But at point J, they differ. So in particular, J could be 1, which means they immediately disagree. That's valid. You can do that. But let's just consider some J arbitrarily in this list. Okay, so our goal here is we want to exchange Cj That's what we want to do. So then we have another optimal solution. It is one less difference between the greedy solution. And so by induction on the differences, we'll get the overall solution. And I'll spell that out in a second, but let's first look at the main exchange part. So can we do this? Can we just exchange Gj for Cj? So think about what could go wrong. What would be an issue? Why wouldn't we be able to just replace CJ with GJ? Hypothetically. It doesn't even have to be real, but hypothetically. Yeah, so GJ would have to conflict with one of CJ plus 1 through CM. So one of these later ones has to conflict with J. Now, why can't that happen? Well, it's the same reason from before. So if that did happen, because GJ finishes the earliest of all the intervals at that point in time, we know CJ has to end later. So for either CJ plus 1, etc., are over here, they have to finish after CJ. But then obviously they don't conflict with GJ either. So that part's fine. But if you had some CJ plus 1 over here, that is a problem. But again, that contradicts the choice of GJ. So if this happened, this would contradict GJ finishes first at that point. And so it doesn't conflict with the C's. Also, we know GJ doesn't conflict with the other things because the greedy algorithm chose them. And the greedy algorithm never picks things that conflict with the past choices because it removes everything that conflicts. So by definition of GJ can't conflict with the past. And by the exchange argument, or by the argument in blue, can't conflict with the C's, and so there's no conflicts. If we remove CJ and replace it with GJ, then this solution, S prime, has no conflicts. Okay? So it's a valid solution. And it has one fewer difference with G. And so the induction hypothesis implies there exists an optimal solution, S double prime, where S double prime contains G. It's a little rough. The base case, well, let me ask you, what's the base case? Think of the easiest base case. Zero. There are no differences. So if there's no differences, S equals G, or at the very least S contains G, and by assumption, S is optimal. So trivially, there's an optimal solution that contains G. So in the base case, by assumption, we have a solution, an optimal solution that contains every greedy choice. And then by induction, we can always take a given optimal solution, replace the greedy choice to get another optimal solution. And so that's one optimal solution with one fewer difference. And so by induction, we can keep swapping to get an optimal solution that contains all of G. So if you unroll this, it's really an algorithm. This is an algorithm to convert any optimal solution into one containing all greedy choices. So I just want to point that out, that this proof by induction is also an actual algorithm for constructing this solution set S. So this proves that there exists a solution set that contains all the greedy choices. And then by this argument up here, it not only contains them, but it's exactly that. So there's no extra ones from that argument. So greedy is optimal. But unlike last time, greedy is not uniquely optimal. There could be many valid choices that are still optimal. So it's just one of them. It is a optimal solution. Okay, any questions about course scheduling? You should be wondering, what's the running time? So the last thing we have to do, now that we have a clear and correct algorithm, is analyze it. So for the most part, all we're doing is sorting things. The main work is sorting, which is O of n log n. Now the issue is computing the conflicts. So the most brute force way to compute conflicts is just to check every other interval and ask, does this interval conflict? Just using the formula for conflicts right here. So if you do that, that's going to be n squared, because you're checking essentially each pair of intervals. But if you check intervals using this clever way, then it's only O of n, and so the whole thing's O of n log n. So the clever way here is, because you know they're sorted, the way you can check an interval is you just check if its start time is after the previous finish time. And because you're considering them in order, you never have to check other pairs. There's no reason to check a pair way over here because it's sorted, so you know that's not an issue. It's way over there. You only need to consider the things nearby. But yeah, that's the idea. Yes? It's O of 1 per iteration. So it's O of n total. So if you're just looking at a specific interval and you wanted to ask, does it conflict with a past or the very last? So let me just write this down. So let's say you're at interval I and you want to check if it conflicts with interval j, which was the last chosen by greedy, then by definition of your sorted order, you know that f of I is after f of j. So you really don't need to look at the finish times. You have additional information. You know it looks like this picture. So you know it looks like this is j and this is I. And so all you have to compare is the start time, that is a horrible j, the start time of this j with the finish time of this I. If you know the start time is after the finish time, like highlighted there, then you know it's non-conflicting because it's moved to the right. On the other hand, if the start time is before that last finish time, you know it's conflicting because by definition that finish time is after that finish time. So this will definitely be conflicting. So in only O of 1 time, you can check a specific pair is non-conflicting just using that if statement. And then because you're just, iterating over every particular one, you're just doing O of 1 n times. So again, we get an O of n log n algorithm. It's pretty fast. Any questions on course scheduling? Okay. You'll get a lot of practice with course scheduling, so I'm not too worried. So let's just summarize what we've done so far. So there's 3 main steps. And this is called an exchange argument. This is the general technique to prove any greedy algorithm is correct. There are other ways, but this is kind of the most general one, so you can kind of use it as like a tool in your toolbox. So to prove the greedy algorithm is correct, you start by assuming there's an optimal solution that is different from the greedy one. You pick out the first difference, so that was GJ before. Or for the tape sorting, that was A and B. They were swapped. And then you need to argue that if you exchange the optimal choice, CJ, for the greedy choice, GJ, the value of the solution is not worse. So in particular, in the past ones, we were looking at sets. So we showed the size of the new set was equal to the size of the old set. It didn't get smaller. And so then by induction, you can exchange them all, and so you get an optimal solution. So specifically, there exists an optimal that contains the entire greedy. And then you can directly argue it's actually equal. So then you can make it equal by direct argument. Okay. So that's the theme. You take some optimal solution O that's different from G. You look at the first difference. You show you can exchange them. And this new thing, O prime, which is the exchanged one, has the same value. So you need to show the value of O prime equals the value of O. Or if you're doing like a maximization or a minimization, this might be an at least or an at most. It doesn't matter, but it'll be something. Now, writing value here, because it's not always the size of the set, like in axis times, it was some kind of sum over times. So it depends on whatever you're optimizing over. That's your value function. Okay. So any questions so far? Otherwise, this is basically the end of the greedy chapter. There's an example called Huffington codes and stable matching, which are like extremely famous problems in computer science, so I recommend you read them. I might do a video on Huffington codes, maybe, I don't know. But if I don't, make sure you read them because they're really, really cool. So any other questions? Before we try a really intense example of greedy algorithms. Okay. So now from this point forward, we're basically doing graphs for like the rest of the semester. But today we're going to focus on greedy algorithms for graph problems. And we're going to look at the minimum spanning tree problem. So you might want to refresh your memory on chapter 5 of what are spanning trees. Here's an example here. Given any undirected graph, a spanning tree is just a set of edges that form a tree and that spans the graph. So spanning means every single node is touched by one of the edges. And it's a tree means it's connected and acyclic. So they all touch each other and there's no cycles. So connected acyclic. And pretty much from now on, forever, we'll always weight the graph on its edges. So we had weighted node problems for some of the homeworks, but these will always have edge weights. So 5 is the edge between U and V. So the weight of UV is 5. That's how you'd write that mathematically. And our goal is picking these red edges so that if we summed up the weights of those edges, they'll be as small as possible. So that's the goal of the problem. Pick the t, or pick the edges in t, so that the sum of its weights are as small as possible. But it has to be a spanning tree, so it's still got to touch every node. It's still got to be connected. It still has to be cyclic. So you just want to find a tree contained inside your graph that touches every node and has this small total cost of weight. So any questions? The weight of this tree is going to be 5 plus 2 plus 3 plus 16 plus 12 plus 4. That's going to be the weight of this tree. Any questions about the problem definition? Okay. Then we'll jump right into the theory. So there is, in general, there could be many minimum spanning trees inside any given graph. All of them could be minimum. You know, they could all, for example, what if every edge had weight 1? Well, then every subtree is minimum. But there's a special condition. If each edge has a distinct weight, then there's exactly one minimum spanning tree. So if every weight has a different edge weight from all the others, then this is the case. So why is this true? We're going to use another exchange argument. We're going to do like 3 of them. They're going to be all over the place. So what's the idea here? Suppose there were 2 distinct minimum spanning trees. We're going to show that there's a contradiction, just like in tape sorting. So you have your trees. They have some edges. So you have T has there's certain edges here. Actually, let me draw this like this. So this is your total graph. This is T. And your other graph is T prime, and maybe it uses some different edges to connect everything. And it can also share some of the edges. But there has to be at least 2 edges that are different. So in particular, there's an edge E that's in T, but is not in T prime. And there's also a E prime that's in T prime, but not in T. And that's just because these are 2 trees, and they're distinct. So there's at least one edge that's different. And if there's one edge that's different, there has to be a corresponding other edge that's different. Otherwise, the other one's not going to be connected. So now we want to prove something about these. So in particular, let's just, for simplicity, let's just assume the weight of E is smaller than the weight of E prime. So now what are we going to do? Well, let's consider a new tree, T double prime. That's T prime, where we're going to remove E prime from it. So if we remove E prime from this tree, it's going to be disconnected, right? So in particular, let's just think about adding E first. So if we add E, there's going to be a cycle. And you can see it in the picture there. So there's a triangle there that forms a cycle. And this is always true. So I urge you to prove this. It's in the chapter 5 section. The idea is if you have any tree and you add a single edge, a cycle has to form somewhere. Okay, so you have this cycle here that has E on it. And so in particular, there's another edge, E double prime, on it. And E double prime is in T prime, but it's not in T. So that's actually a bad example of an E double prime because it's totally in T. So let me find a better E double prime. This one. So why does this E double prime exist? Because we have a cycle, and any cycle has to have two edges connecting both sides of the cycle. So you know E's on the cycle, you know E prime's on the cycle. Well, there has to be a third one. We don't consider these to be cycles. That would just be a hypergraph or a multigraph. So there's this third edge, E double prime, and now what we're going to exchange, we're going to remove E prime from the tree. We're going to add E to the tree. And this is a new tree. It's a totally new tree. Now let's look at the weight of T double prime. It's the weight of T prime minus the weight of E prime plus the weight of E. And what do we know? The weight of E is smaller than the weight of E prime. So this is smaller than, this difference is smaller than the weight of T prime. So this new tree, T double prime, it's a spanning tree. Why? Well, we added one edge in, we made a cycle, and then we broke the cycle by removing E prime, but everything's going to still be connected. So this is a spanning tree of weight smaller than an optimal spanning tree. So how is this possible? What has to be true? This has to actually be an equality for this to be true. It can't be strictly smaller because then that's not a minimum spanning tree. It's a contradiction. So if that's equal, this has to be 0, right? So that implies the weight of E prime equals the weight of E. So in particular, remember we assumed these were in different trees, but now we proved they have equal weight. So because these were different edges, and by assumption we have distinct edge weights, these should have had strictly different weights. They couldn't have been the same, but we proved they're the same. So that's a contradiction. So again, we have an algorithm. We picked two edges, and we actually showed they're equal. And so we're going to, by induction, continually take pairs of edges and show they're equal until every single spanning tree is equal to this spanning tree T. So this proves there's a unique spanning tree T of minimum weight. Okay? So the theory is not super important, but just another exchange argument. E double prime we didn't actually need. I think we need that for a different proof. Sorry if that was confusing. Okay. So this says if there's distinct edge weights, we have a unique minimum spanning tree. Now I claim you can always make the edge weights distinct artificially by just having a preference. And so this is a function that implements a tie-breaking rule. And so it's kind of virtually making the edges distinct. So basically, if one weight is smaller than the other, we take that one as the smaller. But if we ever have a tie, then we're just going to compare the indices of the edges that define the edge. And then we use that to break ties. So in this way, we artificially make all the edges have distinct weights. So the takeaway is we can always assume there's a unique minimum spanning tree in a graph, and this will make the algorithms for computing them easier. So any questions about that? The way that ties are broken doesn't matter. You can break them in many ways, but this is just one example of how you could break ties to artificially make all the weights distinct. Cool. So this is every single minimum spanning tree algorithm. So just like whatever first search, you can kind of encapsulate all the different algorithms for minimum spanning trees into one general framework. So the idea here is we have our graph, and we're going to keep a spanning forest at all times. So the spanning forest could look like this. This could be one of the trees in the forest. Maybe we also have this. So actually, let me draw it like this. This is the full graph. And then these are the edges in the forest F. These are edges in the forest F. These are edges in the forest F. So we have this forest F, which is just a collection of trees. Or you could think of it as collections of edges that don't intersect. So we have these three components of the forest. And at each point in time, we're going to grow our forest somehow. So we always keep this F that's a valid forest. In particular, this forest will be contained in the minimum spanning tree. So that's something that's an invariant that we have to maintain. So typically the way we're going to do this is by considering safe edges. So what's a safe edge? A safe edge is the minimum weight edge that has one endpoint in a component of F. So in the picture above, this is a safe edge if this edge E has min weight. So some alternative choices would be this edge. That's actually the only two choices I see. So these are the two options based on the definition. So both of these edges have one side, one node in F, and then one node not in F. And you're going to slowly grow them. And actually, the definition also allows you to do things like this. So the main thing you can't do is you can't do this. So this blue one right here, you can't do that. So that's connecting two nodes in the same component of F, but it's not one of F's edges. So we can't use that. Those edges are called useless. So this is an example of a useless edge. Whereas E is an example of a safe edge, assuming it has min weight between itself, E double prime, E triple prime, etc. So for example, maybe that's 2, this is 6, this is 100. If that's the case, then E is a safe edge. Okay, so any questions about safe edges? They just connect two different nodes of the graph where at least one of them is in the components of F, but not both of them. They can't both be in the same component of F. And it has minimum weight. So in particular, what does a safe edge really mean? Well, a safe edge is an edge that's safe to add to our forest. Because it's of minimum weight, the greedy intuition says it should also be in the minimum spanning tree. One of these edges have to be in the spanning tree because the graph has to be connected, so just pick the smallest one. And that's basically the greedy algorithm. spanning tree of G, the minimum spanning tree of G contains every safe edge. So the algorithm you'll always use, I didn't write it, but the algorithm is just add safe edges and then recurse. So that's it. So at each point in time, you'll have some set of forests that you're maintaining, and you always know that they're contained in the minimum spanning tree of G. You find a safe edge, or multiple safe edges. You could do it multiple at once. You add the safe edges to your F to build a new F. You're growing your forest. And then you recursively add even more edges to F. And you keep doing it until F is a tree. So once your forest is connected, it's a tree, and you're done. So any questions on the algorithm? Cool. So the main proof of correctness for this algorithm, which is a greedy algorithm, is to do an exchange argument. So we're going to do another exchange argument. And the idea is almost the same as the previous one. So you're going to take some tree T, or your forest. So you have your forest. You have your components of the forest. And maybe you have some edge here. That's safe. And the idea here is if you had a tree, let's say your minimum spanning tree, T, did not use E. So if it didn't use E, in order for it to be connected, it had to connect to this other component. So let's call this component C1, C2, C3. So if it didn't use E, it had to use some other edge, E double prime, to connect to C3, right? For it to be connected. So the whole point here is E is a safe edge. So by definition, the weight of E has to be smaller than the weight of E double prime, or sorry, E prime. I don't know why I put a double prime. Because E is safe. Right? So that's just definition of being safe. So if we took T and we just removed E prime and replaced it with E, well, the cost of that tree, let's call this tree T prime. This is just the cost of T minus the cost of E prime plus the cost of E, and that's going to be smaller than the cost of T. Just by this inequality. So that's why safe edges work. This is the greedy exchange argument. If the minimum spanning tree did not use the safe edge E, it used a different edge, E prime, and you could swap these two choices to get a better tree. So here's the picture. So here, the black vertices are in some subset S. You can think of S as like our current forest, or it's just any number of nodes in the graph. If the minimum spanning tree did not use the safe edge E, then we can remove it, add that E. Clearly it's connected still, because we just changed how we connect the graph, but now it's using smaller weight. So that's the entire idea. So any questions on that? Is the idea clear? Now I'm really paranoid where E double prime comes from, because I feel like it's somewhere. But the picture says no, so I guess it's in a different proof. So any questions on this? This is also an exchange argument, because we started with an original T, which was optimal. We showed the greedy choice improves or does not hurt our cost. And so we can safely, continuously, as an algorithm, replace every e prime by an e inductively until t becomes exactly the greedy tree. Okay. So it's the same kind of idea from before. We're just messing around with trees now. So any questions? Yes? So there's two parts of it. First, let's assume there exist edges. So I'm assuming G is connected. That's an important assumption. So if G is connected, and we have two components, C1 and C2, there must be an edge that goes between them. Or there's some other edge that goes to a different component and then goes there. Either way, there exists a path from C1 to C2 because G is connected. So there exists some path to get from C1 to C2. And then the idea is, if this is your forest F, there's always exist edges that leave your forest. Otherwise, the tree is disconnected. So if there are no edges at all, G is not connected. So we know there exist edges. And then because the weights are distinct, there exists a smallest edge. So G connected implies there exists edges that leave your forest. And then the edges having distinct weights, and they don't even really have to be distinct, but just for simplicity. So let me call this set of edges leaving your forest EF. So then there exists an edge in EF of smallest weight. And that's just because it's a finite set, so there exists a smallest. So for example, EF could consider edges E1 through EK, and maybe the weights are like 3, 2, -7, 6, so -7 is the smallest weight. So first you need to show there exists a set of edges leaving F. That's just because G is connected. Then there's a smallest one just because you have a finite number of elements. Technically it's the well-ordering principle of integers, but please never say that on a homework or exam. It's too much math for this course. Okay, does that answer the question? I hope so. Any other questions about the proof? Okay, then I guess one last thing I want to say is there's a bunch of different types of these algorithms. One type is you grow the forest one edge at a time. In particular, you're going to pick the best edge leaving the forest and recurse. It's kind of the same idea as what we were thinking of before. Or, like we did with intervals, you can just sort all the edges by weight and then go through each edge in order, try to add it. If that would form a cycle, don't add it, and just keep going in order. So these are the two main algorithms for MSTs. Add the safe edges, or sort them and then try adding them in order as long as they don't form a cycle. Cool. So we'll go over these a little more in detail, probably in a video, but those are the main ideas. It's pretty much all of MSTs. Any questions?